In this video, we're going to start to talk about slope fields. I don't know about what you were like when you were a toddler, but me, I kind of jammed on connect the dots puzzles. It was just kind of cool that you could make art by counting and drawing straight lines. And when you were done, it's like, wow, how did they make that into a balloon? I don't know. Nowadays, I think that toddler me wasn't all that bright, but he had his gifts. Anyway, slope fields are going to be doing the same basic idea of drawing straight line and creating a little bit of art, maybe, if that's what you're into. Let's take a look at it. Hopefully you'll kind of get a kick out of this the same way that I do. So what we're going to do is it says here that a slope field is a pictorial representation of all the possible solutions to a given differential equation. So basically what we're going to be doing is we're going to be solving differential equations or analyzing them, but we're going to be looking at the graph rather than the algebraic expression of the function for the most part in this thing. So remember that a differential equation is the first derivative of a function. F prime of x or dy dx is equal to something. I'm going to correct this a little bit. This is what we would call a first order differential equation. There are actually fancier differential equations that deal with the second derivative or the third derivative of a function. They get more complicated. We're just not going to touch them in this class. Thus, when we talk about the solution to a differential equation, for instance, we're about to look at dy dx equals x plus 3. When we're talking about the solution to this differential equation, the solution to that is a function or a bunch of functions. We're saying what function has x plus 3 as its first derivative. So this isn't like an algebraic equation where we're solving for a number. Here we're looking for functions, which can either be expressed as f of x or y. They're making the point here. All right, so let's get to this example. There is an infinite number of solutions. There are an infinite number of solutions to the differential equation dy dx equals x plus 3. So pause the video and show your work here. This should be routine stuff. We've been doing it for a good part of this semester. Well, basically what we're saying here, when we say that dy dx is equal to x plus 3, we're saying what are all of the antiderivatives of x plus 3? And so we can say that y is equal to, what's the antiderivative of x? Well, that's x to the first power, so it's going to be x squared, and then we divide that by 2, which is the same as multiplying it by 1/2. And then plus 3 is going to be plus 3x. And then remember, we always need to add this numerical constant here because the derivative of this would be x plus 3 no matter what real number big C was equal to. All right, so explain why. So this is a solution for any real value of C. All right. And what I want to do is I want to stop right here. This is stuff that we've been really familiar with over the course of this semester, as I say, but I want to express this graphically and kind of give you a picture of what this looks like. So let me go over to GeoGebra. And so 1/2 x squared plus 3x plus c is just an upward facing parabola. So here is what that looks like when c is equal to 0. But the solution, all of the solutions to this are just if we vary the value of big C. And so I can kind of make this do a little animation here. And every one of these parabolas is its own solution to the differential equation, just with a different value of C, as C is kind of the y-intercept here. And if we drew all of these parabolas, we'd see that they kind of filled up the plane. All right, so every point on the plane is a member of one of these parabolas. And so we kind of have a whole series of these solutions kind of filling up the plane. So that's the kind of picture that should be in our mind as we go forward into slope fields. Slope fields aren't going to look quite like that, but we'll see examples of it starting in the next video about how we can start to build them and then play with them to get solutions to differential equations without doing quite the calculus that we've been doing up to this point.